All right, let's continue on with our discussion by moving on to an example. It states, what is the critical angle for light traveling in a polystyrene, a type of plastic pipe surrounded by air? So, whoops, wrong side of the pin there. So we are trying to find our critical angle, theta c. So let's look at that equation again. Theta c is equal to sine inverse of N2 divided by N1, okay? And it's light traveling in 1, whoops, going into 2, and this is the plastic to air, okay? I'm just labeling it as plastic, but let's see. Let's go back to figure out what N1 will be. Here it is, 1.49. There we go. N1 is equal to 1.49, and air was 1.000293, I want to say. Let's go back and check. Did it a few times. Yeah, 293. Whoops, too far again. Okay, so we need to confirm that N1 is greater than N2, right? That is our condition here. So is N1 greater than N2? Yes, it is. So we can go ahead and use this equation. So theta c is equal to sine inverse of N2, which is 1.000293 divided by N1, which is 1.49. And let's see what that critical angle is. Remember that we need our calculators in degree mode. Divided by 1.49, and we get an angle of 42.2. Okay, so this is our critical angle for light traveling in polystyrene that is surrounded by air. Okay, so that is our critical angle. All right, so this is what I mentioned at the start of our discussion, is this dispersion of light, okay? This is the spreading of white light into its full spectrum of wavelengths. So I have a few pictures here and a reminder of our visible light range here. So we have a glass prism where we have the incident light coming in, and it'll hit some glass, change direction, and go back into air and change another direction. So this is the idea. Now, if we have incident white light, it will do something similar, right? So we have our incident ray coming in, changing direction, and it'll split up into its component colors. So it acts very similarly to just pure wavelength of light, except it will split into its component colors, okay, or its spectrum of wavelengths, okay. So I just want you guys to understand that this works, okay, what dispersion is, and recognizing that it is present when we have white light that spreads out into a spectrum of wavelengths. So we have, let's see, we also have, looks like this is a rainbow, right? And this is a similar sort of thing. And again, this is the, you can see my thing here, this is a prism that's spreading out into the component colors, okay? All right. So let's look briefly at lenses. This is going to be a little bit in depth, I think, for our course. This is where we're kind of deviating quite a bit, I think. But I wanted to get you guys to understand the basics. Okay, so this is image formation by lenses, and there are two different types of lenses. We have convex and concave. Convex is a converging lens. Okay, so light rays that enter it parallel to its axis cross one another to a single point on the opposite side with a converging effect. Okay, and that single point is called the focal point. So, let's see, don't worry too much about this, just about this guy here. So we have our light rays coming in to this lens. So this is our convex lens. And those light rays will hit it and, of course, be bent because the perpendicular to the surface, blah, blah, blah. And we will have that light change direction, and all of these rays will come to some point called the focal point. Okay, that's what that F is. Where that focal point is, and with respect to the center of the lens, F, so this length here is called focal length. Okay, so these are a couple of terms that I want you guys to know. And so we have then that an image can form here at this focal point, okay, where all of these rays converge, where all of them come together, okay? So this will be where an image can form here, okay? On the other hand, we have concave or a diverging lens, and that is where light rays bend away from its axis. That should say from. Sorry. And so we have our light rays coming in parallel to its axis, and using some geometry or geometric optic ideas, we have that our light rays will trace back to some, again, focal point at some focal length, okay? And you can see that the light rays will bend outward away from its axis, okay? So this is concave lens, where we have the light rays bending away, and our image forms before the lens, if that makes sense. Okay, so our image is forming on this side of the lens where the light rays were coming in the first place. Okay. Okay. So again, I don't want you guys to worry about these two depictions. I should have cropped them out, but worry about this and this, okay? Convex versus concave, the basic idea. And one other thing that the book mentioned, and I think is kind of interesting, that if we have a magnifying glass and sunlight, which we do a lot here in the Central Valley, we can use a magnifying glass to get all of our light rays to converge at one point that are coming through here. All the light rays from the sun coming through here, we can get them to converge at one point, like on a piece of paper, and cause heat. So that's something that's kind of interesting because there's an intense amount of light rays at that one particular point. Okay. All right, so here is a bit more on lenses. So I already mentioned the focal point, F, of a lens, as well as the focal length, okay? And I wanted to also mention optical power. So this is something that we tend to see with our if we wear glasses. A lot of people do. Um, and you might when you're older. That's what I've learned. um, so we want to know what kind of optical power we need to use in order to correct for whatever we're not able to see clearly, right? So this is where optical power comes in, and it's the inverse of the focal length of the lens, okay? So P, optical power, is equal to 1 over F, or 1 over the focal length, okay? And note that the units for optical power are in diopters, capital D, which is 1 over meter, or 1 meter inverse, okay? So however you want to write it, diopters would be good to practice, okay? And again, this is the sort of idea that I want you guys to know which one is concave, which one's convex, okay? So being able to recognize how they act with the light rays, okay? Okay, so this is the end of our lecture, but I included some videos for you guys in the module to kind of get you kind of understanding more on this stuff, which would capture the next chapter as well. I think 26 a little bit. It's the idea of, let's see, eyes. Yeah, eyes and telescopes, microscopes. So I have a video in there as well to kind of get your guys kind of seeing the day-to-day understanding slash why we care. It's pretty interesting, I think, especially for glassware, or any kind of corrective lenses, because a lot of us do have to have this, or eventually will, due to age. So I have a video on that, and I think it's really good, as well as the quiz will include some of those ideas. So this is something that you would see in the future for an exam, those conceptual ideas rather than a lot of calculations. So as you saw through the lecture, these 3 videos, that there wasn't a ton involved with the calculations, but there are a lot of conceptual ideas, and you'll see that more in the crash course videos as well. Okay, so next time we'll start to look at special relativity, and we'll kind of go from there. Remember, if you ever have questions, let me know. I'm here to help you guys. Okay, all right, have a good one.